So recording's good. All right. So welcome to class today, folks. It's week 2. So that's awesome. This week, we're going to start thinking about evolutionary theory. We're going to talk about mechanisms and stuff like that. Next week, it's kind of split into 2 different weeks. We'll start with like pre-Darwinian and Darwinian conceptions of evolutionary theory, and then we'll look at kind of like how it's been reworked and re-employed later on. For those of you that were here and saw I'm going to share my screen really quickly, saw the quote that was up at the beginning. This is from Theodosius Dobzhansky, and Theodosius Dobzhansky is one of the fathers of modern population genetics. It's a really famous quote. He says, "Nothing in biology makes sense except in the light of evolution." He's talking about shared anatomy, genetic patterning, and all of that stuff. And something that's kind of cool, just to point out, I'm going to switch to share really quick. So anthropologists really we're all about like kinship. And so there's a website called BioAnthTree where intellectual kinship is tracked. And so I trained under Jonathan Marks. So he was my master's advisor. My dissertation advisor is Michael Cepek, who's not a biological anthropologist. John Marks trained under Steve Zagura. Steve Zagura trained under Richard Osborne, and Richard Osborne trained under Theodosius Dobzhansky. So if John Marks is my academic father, then he's your academic grandfather, your great-grandfather, great-great-grandfather, great-great-great-grandfather. So intellectually now you are directly related to Theodosius Dobzhansky. Another person that you are directly related to is, I will show you. So I trained in primatology under Linda Wolff. Linda Wolff is one of the people that invented ethnoprimatology, or the study of human primate relations. She trained under Paul Simmons, who trained under Theodore McCown, who trained under Alfred Kroeber, who gave that quote that you saw last week that said, anthropology is the most humanistic of the sciences and the most scientific of the humanities. Alfred Kroeber trained under Franz Boas. So not only have a direct intellectual lineage to Theodosius Dobzhansky now, the father or one of the fathers of modern population genetics, you also have a direct intellectual lineage to the father of American anthropology as an entire discipline. So you're in good company. All right, I'm gonna stop sharing now. All right, I just thought that'd be interesting. I noticed I have a quote from Theodosius Dobzhansky on this slide. I should show you how you connect to him. All right. So my plan for today, as my phone just keeps ringing over and over again, the last screenshot. All right, so the plan for today is going to be to just kind of say what we're up to this week. Looking at the Canvas page, we will talk about the Gregory article first. The evolutionist fact theory and path. I think it's a really important article. It's really important to understand these concepts, because really the article, it's less about evolution and more about like what these words mean in science. Different fields have different terminology, and these terminologies have very specific meanings in many cases. And then we'll see if we get to talking about the Zader article. We have time on Thursday to do that. Then I have like a little PowerPoint that we can kind of talk about together. And this is the class period where I really want to think about the conflict that exists between evolution and religion. We talked about it a little bit last week, and I mentioned the book that Jonathan Marks, who I just pointed out, just published within the last month. That engages in that topic. Specifically, I think about it a little bit differently than him, but his approach is still really, really interesting. And I think the big contribution of that book is he makes a really compelling argument that the conflict doesn't actually exist between evolution and science, because evolution is just a process that's ongoing, and scientists that employ evolution use it as a tool. And so they're not really kind of fighting over that kind of stuff. It's really a theological debate between creationists, or people that believe in a literal 6-day creation, the world 6,000 years old, which actually itself is not. The 6-day creation is in the Bible. Maybe it's complicated because of the translations to other languages. We can talk about that too. But the 6,000 years old is not. That was by a monk that basically did some math with all the begats, and then concluded it. So it was a kind of a literary study, so to speak, to try to determine that. And has nothing in the Bible that says anything about how old the universe is, or the world is, or anything. Then I will unpack it from my standpoint, or the way I think about it in my studies of the topic, doing my philosophy degree, and then just being an anthropologist and using evolutionary theory. And then that should get us to the end of the class. Hopefully we'll have some really good conversations today. We'll talk about the cake metaphor. We'll talk about the cake metaphor today too, I believe. So I'm going to share my screen again, just the Canvas page. So we're here at week 2. And this week we're just thinking about evolution. So we're not talking about really mechanisms, although we can talk about natural selection a little bit when we're talking about the Gregory article. We're really just kind of thinking about when we talk about evolution, what is it that we're actually referring to? And then we're going to unpack these important concepts in science, fact, law, theory, and kind of what they mean. And when we say something like evolutionary theory or theory of gravity or germ theory, what work is the word theory doing, and what does it actually mean? But we'll get there. So you got 2 readings that you should be doing this week. Hopefully you read the Gregory article up to this point, or at least skimmed through some of them. The Gregory article is really short. The Zeta article is a little bit longer, but it's the first time I've ever taught it, but I really like it a lot. And then you've just got, I know, a list of things to turn in last week. This week is just the reaction statement. I was really pleased overall with the quality of the submissions on the reaction statements. Some of the things that need a little work are going to be things like citing, being a little bit more specific. And the reason that I asked for specifics is because I want to understand your thought process. So a lot of you did a really good job, even though you didn't cite specifics, you reacted to the reading, but I want you to take it a step further and also bring in specifics, because I want to see what things from the readings are leading you down the road that you're taking kind of intellectually and the thought process. I've given you everybody that's turned it in, your week 1 reaction statement. I've given you feedback already, so please go to your grade book in Canvas, look at the little speech bubble, click that, and you'll see my comments. Some of you, it's just going to be this is what I saw you do, and it's really good, so keep doing it. For others of you, it's you did this really well. Let's work on this next time. So we're going to, just make sure you look at that before you write your second reaction statement, just so you can take my feedback. Part of your kind of overall grade for the course, just to remind you, is your ability to take feedback and use it. All right. So any questions about just kind of the structure of the week, or how we're going to do class today? Awesome. I'm going to stop sharing really quick. Not new share, stop share. There we go. All right. Well, if you have any, obviously, please use the chat if you do have any questions, or just interrupt me. Either is fine. So I do want to hear questions. It's my favorite part of class is you asking questions, or having ideas to talk about. So let's talk about the Gregory article really quick. And let me just make sure that I don't have, I do have a slide in here about that. We'll get to it when we get to that part. So obviously, your reaction statement isn't meant to be done yet. If you've started reading, that's great. If you haven't, don't be embarrassed or anything. It's Tuesday. Your reaction statement's not due till Thursday. And if you had set time apart, like later today or tomorrow or Thursday to work on your action statement, that's cool. But let me just check with you all. Has anybody read the Gregory article yet? I can't remember if anybody turned in the reaction statements. I'm teaching 2 classes, and so it's hard for me to keep up with like which classes have people turn stuff in like way early. I don't think anybody has in here, but I don't actually remember. I guess I could look instead of being ridiculous. No, nobody in this class has turned their reaction statements in. Not I. Okay. All right. So all right, I'm going to share my screen. I'm just going to share the article itself so we can kind of talk through it, because this is, I'm normally not going to walk you through an article. But I do think this is a really important article because there's a lot of confusion that often occurs around this language. I'm going to zoom in a little bit. And so yet again, this is a really short article. It's like 7 pages with citations. So whatever, it's 6 pages long, super short article. And the main point when you go to read this that I want you to pay attention to is this defining terms. It's really important to understand what these words mean when they're used in a scientific context, because they often mean something different from what they mean in kind of our everyday common colloquial speech. And so I'm going to pull the chat up just in case anybody answers here. But let's start with fact. Let's not talk about how Gregory thinks about fact here or like how he's defining it. But let's think about how we commonly use the word fact. What does fact mean if you say, like, I know this for a fact? What are you meaning by the word fact there?
Like, something that's like concrete. It's not biased or anything like that. It's like concrete, I guess you could say, evidence of something, I guess.
Yeah. And John is basically echoing you, irrefutable evidence that proves or supports a statement, right? Like it's a fact that we're all on Zoom right now. Exactly. And the way that we use fact in our common speech is basically the same way it's used in science. And so there's a couple of definitions here for fact. There's the one from the National Academy of Science. So like the big kind of United States thing, and they just say it's an observation that's been repeatedly confirmed for all practical purposes is accepted as true. That's a really good definition, but I really like Stephen Jay Gould's definition, which is a fact can only mean confirmed to such a degree that it would be perverse to withhold assent or provisional assent. And so, oh, no problem. Thanks for letting me know. And you guys don't have to pull the article up at all. So what Gould is saying here in his Gouldian speech is that like facts are something that we, as the NAS is reporting, it's been repeatedly confirmed. It's been confirmed so much that it would be ridiculous not to accept it as being true. Perverse to withhold provisional assent. So it doesn't mean facts are like necessarily irrefutable, but it also means that facts aren't like easily argued. And so things like the sun revolves around the earth was treated like a fact, when in fact the facts that backed that interpretation up are the sun moves across the sky. That's the fact. Now the sun rotating around the earth was an inference based on that fact. And he doesn't talk about like inferences and stuff in this article too much. He mentions it in regard to theory, but inferences are important. And actually on Thursday, we're going to work on inferences. We're going to do an activity in groups that asks you to think about the facts about an observation about a particular site, inferences that you can make from those facts, and then what further questions do you need? And then we'll kind of talk through that. So fact, that's the definition. The way that you all said it, that's the definition of fact. Irrefutable evidence that basically demonstrates something's true. And facts tend to be really boring. They're just like what you observe is happening. So like if we don't observe the earth rotating around the sun and orbiting around the sun, right? What we notice from our position is the sun moves across the sky. and the moon moves across the sky, and the stars move across the sky, but we don't. So that's the fact. We don't observe unless you're away from Earth. Like we have sent out probes that have then looked back and seen stuff. But nonetheless, facts. Basically, when we say fact in English in your common speech, is basically the same thing that science means. I'm going to skip over theory for the time being. We'll come back to that because that's the one that people mess up the most. Yeah, Earth being round is a fact because it's something we can observe. And then we can observe also the consequences of the Earth being round, like the Coriolis effect. So if the Earth was flat and didn't rotate, winds, because it's cold at the poles and it's warm at the equator because the sun hits the equator and warms it up, and it's colder at the poles. What that does is it causes air to circulate. It's the same way it's the same way your air conditioning system, like your house, works. So you have coils on your air conditioning system that put the liquid through it, and that liquid then warms up as it moves through the house. And then when it comes back through the coils, it releases heat, cools back down, and keeps your house cool. So if the Earth was flat and didn't spin, the cool air would circulate towards the equator and then circle right back up to the poles. So from the south and the north. We're in the northern hemisphere, so I'm just going to do it from our perspective. But what actually happens is winds that come, or not winds, but the air currents that come down, they don't move straight south and then hit the equator and then move back north. They go they go south and they curve because the Earth is also spinning at the same time. So it's causing those currents to twist. So I think in the northern hemisphere, they all twist they twist in opposite directions, basically. The southern hemisphere air currents and the northern hemisphere air currents. I think the northern hemisphere twists to the right and the southern hemisphere twists to the left. It might be the other way around. I don't remember off the top of my head. But Coriolis effect is something we can observe. You guys are so hilarious in the chat. Yes, and also people have known the world was round for thousands of years. In ancient Greece, they actually, oh my gosh, a natural philosopher in ancient Greece determined fairly accurately, only within a few thousand miles off, the actual circumference of the Earth by basically triangulating, looking at the length of shadows based on how close and far from the equator they were in Greece. So this is something we've known for a long time. So yes, so we know for a fact that the Earth is round, and there are inferences that we can make about how things happen based on the fact that we know that the Earth is round. And then there's just a ridiculous amount of evidence. Let's talk about law next. So when you hear the word law, just in common speech, what do you think of? What does it make you think of, or how would you define it? Rules set by society, yeah. So these are prescriptive laws, and that's actually one of the things that Gregory talks about here. If you hear something's a law, it's a rule that's set by society, right? Like by a government or by your house. Laws tend to be codified, written down, makes them a little bit different from rules, I guess. So these are prescriptive. Prescriptive means they tell you what you can and can't do. Exactly. So when we hear, you guys are nailing it. When you hear law, that's what you think of. In science, laws are not prescriptive. Laws are descriptive. So they don't tell you what can and can't happen. They describe what's going on. So laws of motion, for instance, are describing what happens when objects are in motion or at rest, right? So if we think about the law of gravity, the law of gravity basically describes what happens when you release an object. I don't think the Murphy's law is a real law. It's a thought experiment, I believe. So let me just I'm going to grab my AirPod case because it's the closest. Actually, that's way too dark. I'm going to grab the capo from my guitar. It's darker color. So if I drop this capo, it will fall, right? and the law will describe what happens when I let go of it. So given the mass of the earth, this capo will accelerate towards it at 9.8 meters per second squared, or 9.8 meters per second per second. That means the same thing. So that's the law. The fact is, and let's think back about facts. The fact is, if I let go of this, it will fall, right? That's the fact. It's kind of boring. There's nothing like particularly profound about it. It's just what happens. It's an observation. When I let go of this, it falls. The law describes what happens when I let go of it. So the fact is just the observation. The law is describing the occurrence. And the theory, let's jump to theory now. When you think of the word theory, this is absent from friction and air, like a feather floats. Yeah, exactly. Yeah, so you have to you can actually take into account air resistance and stuff on an object. And you also have to take in consideration the aerodynamics of the object and whatnot, because there's terminal velocity, so it can't just evenly accelerate. Even like something pointy like an arrow can't evenly accelerate towards Earth at 9.8 meters per second squared. The friction of the air against it will prevent it from reaching that. And if like a body, like a human falling, like skydiving, will reach terminal velocity because the air friction basically balances out. So it won't ever like just infinitely accelerate towards Earth. And of course it can't, because there's a ground eventually. So when you think about theory, the word theory, what comes to mind? How would you define it?
I think of like hypothesis, or like maybe
Like a
the
guess, but like
foreshadowing of what may happen.
And somebody else said something too. Matthew, I think it was you.
yeah, like I always kind of consider theory like not exactly like a guess. I mean, like a guess, but like a more like an educated guess. Like I guess has a bit of foundation, but not fully there.
Yeah, exactly. And that's exactly how we use it in our common speech. If you watch CSI, or something like that, something that you think will work but haven't tested yet. See it. That's how they use it. He shows up, and let me get my glasses because I have to do some really like high quality acting now. They show up at the crime scene and they're like, "My theory is he was killed by a gang of kangaroos," or something like that. That's how it's used in common speech. But in science, that's not. Thank you. That was supposed to be incredibly dramatic and not funny, but I'll take comedy. I'm joking. In theory, that's not what science means. Science isn't a theory is not an educated guess in science. They should hire me in CSI. I'd be good at it. I am actually a consultant on a film that's coming out, but later. It's not out yet. It's actually being filmed right now. Yeah, nothing in science is really absolute, right? Facts aren't scientific. Facts are just observations. You don't need to do science to determine facts. You use science to determine law, or to generate laws and theories. Actually, the ultimate goal of doing science is to generate theories. Because if facts are just kind of boring observations and laws are descriptions, theories are the explanations. And theories aren't just like the best guess. Actually, your best guess is going to be your hypothesis. So your hypothesis, the definition that they give is going to be like a tentative statement about the natural world. Where is there? I don't remember where it is, but it's basically a tentative statement about a testable tentative statement about the natural. Here it is, a tentative statement about the natural world leading to deductions that can be tested. So your hypothesis in science is your best guess. Given what you know, it's your best guess. They have to be testable. Theories, on the other hand, are the ultimate goal of science. Your goal is to generate theories. Theories use laws and facts and tested hypotheses and inferences to explain. So facts are just your empirical observations. Laws are your descriptions. Theories are your explanations. The why. Why does it happen this way and not another way? And so the definition that Gregory gives from the National Academy of Sciences is a theory is a well-substantiated explanation for some aspect of the natural world that can incorporate facts, laws, inferences, and tested hypotheses, and sometimes other theories. like the theory of natural selection. You're getting at something that I'll get to in 1 second. Great question. The theory of evolutionary theory includes the theory of natural selection, niche construction theory. It includes theories about genetics. It includes theories about, it includes laws about heredity. So evolutionary theory is an explanation for why change happens over time in populations. And gravity isn't still a theory. It is a theory and also a law and also a fact. So the way that we're taught, these words when we're in elementary school, where, you start with a hypothesis, or you start with like a guess, and then you have a hypothesis, and then you have a theory, and then you have a law, and then you have a fact. That's not what these words mean. They all are getting at something different. Facts are your observation, your empirical observations. Your laws are your descriptions. Your theories are your explanations. Your hypotheses are just part of your research design. So they're your best guess. You start with hypotheses and you test your hypotheses, trying to disprove your hypothesis. And from there, the ultimate goal is to generate theory. So you want a theory that incorporates laws and your observations and facts. So gravity is a fact. If I drop this, it will fall. That's a fact. The law of gravity states that given the mass of the earth, because you have to, laws, I didn't even define laws here, but laws are descriptive generalizations about some aspect of the natural world and how it behaves under stated circumstances. So you have to state the circumstances. So one of the, let me come up with an example. One of the critiques of evolution is that it can't happen because of the second law of thermodynamics, which states that objects will undergo entropy in a closed system. But people, when they appeal to the second law of thermodynamics, they only say that objects, all matter experiences entropy. What they don't get is that in a closed system part, Earth is not a closed system. Where does our energy come from as a planet?
Cool. The sun? I don't know. The sun?
Exactly, the sun.
Oh, okay, cool.
Yeah, it comes from the sun. And your body is in a closed system because you eat and drink, right? And so the second law of thermodynamics isn't applying. It doesn't work because it's under the stated circumstances. So under the stated circumstances, you should not expect bodies to experience entropy or planets or whatever to experience entropy because it's not a closed system. So that law doesn't apply. It only applies in particular situations. So the law of gravity, the fact of gravity, stuff falls. The law of gravity basically describes what's happening when something is falling, when something is under the force of gravity. I mean, we all are because we're stuck to the surface of the earth. The theory of gravity explains why it happens that way. So what causes objects to fall in the first place? And the theory of gravity states that matter has mass. And mass warps space-time. We can think about space and time as one thing. This comes from Einstein. Mass warps space-time. Objects with really big mass warp space-time more than objects with less mass. And planets are really big, and stars like our sun are really big. And so they're warping space-time. So if you think about space-time as being a fabric, like a sheet that you set a bowling ball in the middle of, what happens to that sheet?
It indents.
It indents, right?
In.
Exactly. And then if you drop a baseball, is the bowling ball going to fall towards the baseball, or is the baseball going to fall towards the bowling ball?
The ball to the bowling ball. Baseball to the ball.
Exactly. And so that's what mass does. It warps space-time. And of course, this illustrates that the where the metaphor fails is the indention is at the bottom of the bowling ball. But with space-time and gravity, the indention is at the center of the mass. So it's at the center of the planet or the star or your body or whatever, of all matter. It's at the center of it. And so objects fall towards the center of bodies with mass, which is all matter. So that's the explanation for why gravity works. And we know it works because who here has used your GPS on your phone before?
Yep, all the time.
All the time,
Yep.
right?
All the time.
All the time. And if that was not an accurate explanation for gravity, your GPS would not work. Because remember, it doesn't just warp space, it also warps time. So as you move closer or farther away from a body with large amount of mass, like a planet, time moves at different speeds. And so our satellites that we use for our GPS to work, time is moving at a different speed to those satellites than it is to us because we're closer to the core of the Earth. So we have to calculate that difference in time into our GPSs and into the satellites so that we can get to where we want to go. Because if you're driving from Texas to, I don't know, Texas to Sacramento, California, you're not going to get there. You're going to fall short because you're not calculating the difference in time as it moves from farther away from the body of mass. And also it also is different relative to speed too. So things at light speed experience time differently. The closer you get to light speed, the more differently you experience time. Yeah, we don't really understand. This is an excellent point. We don't really know where space and space-time come from. There are a lot of hypotheses. There's some pretty good explanations for what we see. So, like if you've heard of the Big Bang Theory, it's like probably the way that I was taught about the Big Bang Theory is been heavily amended since. Like I first learned about it because we have better technology to kind of study these things, but it all began basically with looking at Doppler shifts in light. So have you ever been like walking and had a bicycle whiz by you, or a car whiz by you, and as it comes closer to you, it gets more high pitched, as it goes down, it gets more low pitched as it passes you.
That's kind of like sirens.
Yeah, exactly. That's called the Doppler effect. It's actually how we like track clouds instead of heard of Doppler radar. Light does the same thing because light is waves. It's also particles. So as like a car is coming towards you, the sound waves are being compressed. And as it passes you, they're then being stretched out again. So it changes the tone. Well, light has a tone too. And as objects are moving towards you, they are blue shifted, and as objects move away from you, they are red shifted because the light gets stretched. I remember red and infrared are longer wavelengths than blue and violet. Like ultraviolet light is a really small wavelength. Radio wavelengths are really, really long wavelengths. So when we look at the light in other galaxies, we see that they're red shifted. So they're shifted toward the red part of the spectrum, which tells us that they are moving away from us. And no matter which direction we look in, the light's shifting away from us. So we know that's happening. That's like the fact. That's the observation. The interpretation of that fact then is that everything's moving from a singularity. There's also kind of more experiments that I don't really understand because it's not that's not my expertise, but I understand it up to that point. Exactly right. When you're in a vehicle driving, it doesn't seem that fast, but if a car whizzes by you, it looks really fast. Exactly. So yeah, we don't know about space-time. We know that formulation of it works, and our satellites work, and we can do space travel and stuff and communicate across long distances, and we can use satellites to make telephone calls, and we can ping off of satellites, and all of that is thanks to, in a large part, understanding the theory of gravity. So gravity is a fact. Things fall. There is a law of gravity which describes how it falls, and there's a theory of gravity that describes why it works that way. And then we can do stuff with that stuff. Thank you. You're very welcome. I love tangent conversations because I love science. So evolution is exactly the same. The fact of evolution is change happens. Populations change over time. There's nothing particularly interesting about that. We can point to a lot of other facts like gene frequencies and traits change over time. It's a fact that organisms are adapted to their environments. And yet again, they're not particularly interesting. They're informative, but they're kind of boring. There are laws of heredity that explain how traits get passed down. So it describes how heredity works and how, meiosis, mitosis, and how like crossover, there are all kinds of genetic stuff we can talk about. I don't want to get too deep into that because we're really getting into the weeds. And then the theory of evolution, or evolutionary theory, is like why it occurs that way. So one part of evolutionary theory is natural selection. And natural selection is the explanation for how organisms become adapted to their environments. And in short, it's like super intuitive, and I don't know why nobody ever gets taught it this way. But there's kind of 4 things to natural selection. Living, surviving, and reproducing is really hard. Not everybody does it. Can we all agree on that?
Yes.
Yes. I mean, yet again, this is boring. 2, there has to be variation in the population. Is there variation among Texans or among humans in terms of their bodies?
Yes.
Yeah.
Yes.
Height. Yeah, we can point height, hair color, skin color, eye color, lactose intolerance, any trait we wanted to point to, we could point to, right? So there is variation. That's number 2. Number 3, variation has to be heritable. If you have tall parents, do you tend to be tall?
Yes.
Yeah. If you have dark-skinned parents, do you tend to have darker skin?
Yes.
And light-skinned parents, lighter skin.
Mhm.
Exactly.
Makes
Yeah, again,
sense.
this is all this is all boring. Yeah, there's definitely recessive phenotypes. Hair color, eye color, skin color are really, really complex. There's like 37 genes associated with the development of skin pigmentation. So that's a really big thing. So it doesn't work in Mendelian, but there are traits that are highly Mendelian. Eye color is not one of them, even though it's the one you're taught. There's a lot. I think, I can't remember off the top of my head. There are many genes that are implicated in the development of your eye color alone. So we taught Mendelian, when you do the Punnett squares, if you remember back to high school and you did that. And we always do it with eye color. If you have a parent with blue eyes, recessive, and if a parent has, dominant recessive, and then you get recessive, you can have blue eyes, dominant recessive, brown eyes. Eye color is a little bit more complex than that, but it's how you learn heredity basically in school. Melissa, would you want to say something? I'm sorry, I was rambling.
No, I'm sorry. I didn't realize I was not on mute. I'm sorry.
Oh, no problem. I just want to make sure I'm attending to you.
Okay, thank you.
Yep. So that's 3, right? So living and surviving and reproducing are hard. Not everybody does it. There has to be variation. That variation has to be heritable. And then some of that variation confers a reproductive advantage. So like if you are better able to hang on to a branch, to walk out, to get to an insect, or to get to some fruit, or if you have color vision and you can tell the difference between ripe fruit and unripened fruit, right? You are more likely to select the right fruits and thus have more energy. Yeah, maybe if you're tall, you can reach up. That's not something happening in humans, but definitely is like, think about giraffes, right? Giraffes can reach food resources that other animals can't because they have long necks. And so they have less feeding competition across kind of the many browsers that live in the savannah. So those are the 4 things of natural selection. Surviving and reproducing are hard. Variation. So we already said yes. Variation, we said yes. Variation is heritable, we said yes. And of course, as Zach pointed out, I mean, there like some traits confer an advantage. So reproductive advantage can be, breeding members of your species find you sexy. So I'm assuming these traits that are independent, they're not for humans. So humans, we think about biocultural evolution, and we'll read a really interesting article a little bit later by John Marks called The Biological Myth of Human Evolution. He's saying we can't understand human evolution simply as a biological process. We have to understand it in relation to biology and culture. So the 4th is some of it confers reproductive advantage, and this is true. And as a consequence of those 4 things, adaptation occurs. So if some organisms are better suited to their environment, They are better able to exploit food, attract mates, whatever. Yeah, maybe growing hair on the face. Of course, like facial hair itself is probably was probably ubiquitous at the time, and there were changes that happened. We don't exactly know because facial hair doesn't fossilize, but we do have facial hair now. So it could have evolved as part of sexual selection. It could just be a spandrel, just a consequence of other things changing, and then that just being kind of hanging on, piggybacking on it. We don't really know for that kind of thing, but generally, right? So those four things happen, adaptation occurs. So we think like the way they talk about natural selection is just like somebody doing the selection, but there's nothing doing the selection. The selection is a consequence of surviving and reproducing being hard, there being variation, which is heritable that confers reproductive advantage. When all four of those things are met, natural selection occurs. There's three kinds of natural selection. We'll talk about that stuff next week though. But anyways, the whole point of that is to move us from thinking about gravity, the theory of gravity, to evolutionary theory, which is the explanation for how things change over time. Part of that is adaptation, but not all change over time is adaptive. And so there are other processes that are ongoing, and we'll talk about those over the next couple of weeks. But other things, we're living in a pandemic right now. The way we're able to study that is because of germ theory. So the fact is we get sick, right? We all agree with that? People get sick.
Yes.
I'm going to say yet that you all agree because we're living in a pandemic, so you know it. The fact is people get sick. The theory is, why do people get sick in certain ways? Obviously, you can be sick from cancer or whatever, but germ theory states that there are microorganisms that get into your body, and as a consequence of that infection, there are particular immune responses to it, which then express themselves as symptoms, right? So germ theory is an explanation for why we get sick in certain ways, that being infections. Coronavirus, the flu, MRSA, staph infections, any of that stuff. And there are previous explanations like miasma, the miasma theory, which was that bad smells made you sick because people correlated like bad hygiene and live like in London where people are just literally throwing their shit in the streets. I don't mean like their garbage and trash, which they also did. I mean their feces into the streets, especially in poor areas where they didn't have good drainage. And then like all these areas smell bad and people are more likely to get sick here. What they weren't able to understand is that what was making them sick was the microorganisms that were being bred due to being unhygienic, not the smells themselves.
Not the smell, right?
Yeah. So we have, there's theories for all things, like pretty much everything, because they're the explanations, and it's the theories that we use and the laws that we use to then like do stuff, to like make predictions, to solve problems, to invent really cool things. All of those things, they take theories because theories subsume laws. You want to generate a theory that can eat your law and have it as part of it, so that then you have this comprehensive thing that you can then apply and do really great things with, like make vaccines, which might be the greatest invention in human history, or have satellites go up into space, or have GPS. All of those things relied on, or have like radio waves. All of those relied on scientific theory, explanations for how things work, which have facts and laws and tested hypotheses as part of it. So does that help at all?
Yes.
Yeah, I think it does.
Good. I'm going to stop sharing. I hope it helps, because how we use many of these words in our common speech is different from what they mean in science. So when something's a scientific theory, you're referring to a well-substantiated explanation for some aspect of the natural world, not the supernatural world, that incorporates facts, laws, tested hypotheses, inferences, all of that stuff. So it doesn't mean even laws, right? We generate laws, but laws get refined, and we find the bounds of laws. So we think we generate laws, and we're like, okay, they work in all of these spaces, but then we give boundaries to them, right? So like the law of gravity works really, really well, except when you get into a black hole. And now all of that breaks down. And so it's figuring out, and this is just true for any science, whether it's theory or laws, you want to figure out what the bounds of it are, or what the bounds is of your theory or of your law, so it's usable. So if you find like a tool on the beach and you don't know what it's good for, you can't use it, right? So you want to figure out what it's good for so that you can use it when it's appropriate and not use it when it's inappropriate. So evolutionary theory is really powerful. It's a really powerful tool for thinking about how organisms, populations change over time and adapt to their environment and adapt their environment to them. That's part of it too. And to predict like mutations in infectious diseases. And we'll look at an example at the very end. It's a really powerful tool for that. But if you want to take evolutionary theory and then understand how cultures change over time, it does not work at all. So you want to know the bounds of it. What does it work for and what doesn't it work for? As soon as you start setting bounds to something, it becomes more useful. And science, this is just true for science. Science is an empirical study of the natural world. So science cannot answer questions about the supernatural world. So knowing the boundaries of science and the utility of it makes it more useful. So we're not just willy-nilly. If you want to like, hang a picture on your wall and all you've got is a drill and you have a nail, it's not gonna, I guess you could smash it in with it, but it's not a very good tool for the job, right? It's the wrong tool for the job. If you had a hammer, that's the right tool for that job. So knowing what your tools do and how to use them and when to use them, that's like one of the most important parts of being a scientist. For any of you that want to be a scientist, and all of you benefit from science in one way or another. So as consumers of science, it's also kind of good to keep in mind. A lot of talking. So any questions about all of that?
No, sir.
So obviously still read the Gregory article. It's a really good article. It's really short. And the Zadar article, I think that's the like really, really excellent article, because they talk about what she talks about in the article is some history of evolutionary theory, kind of the standard evolutionary theory, or what we might call Darwinian evolutionary theory, or the modern synthesis. And then juxtaposes that to kind of contemporary, what we can understand about evolutionary theory today, which we call the extended evolutionary. There's a lot of different names for it, like extended evolutionary synthesis is what she uses in the article, and it's what I use. But there's like the inclusive evolutionary theory. There's a bunch of them. We're going to go extended, just because the differences between those they're irrelevant. All righty. So Gregory article we talked about. Now, let me look at my PowerPoint. I want to talk about the cake metaphor. Yeah. So I'm going to share my screen, and then we're going to talk about cake. So who here has eaten cake before?
Almost every day.
Almost every day. Cake is delicious. I don't have a way that you can have your cake and eat it too, unfortunately. But this is a really good metaphor for understanding both anthropology and how you can study evolution, or bodies in general, like bodies. People have eaten cake. Some people love cake. Some people eat it every day. What are some ingredients that go into making cake? What do we need? So we want to make a cake. What do we need?
Flour, eggs, water,
Flour, eggs, water, milk. Yeah.
oil, milk.
Oil. Yeah, we need a fat. Let's be like basic and make a vanilla cake. We need baking powder. We need a leavening agent. Absolutely.
Vanilla extract.
Vanilla extract. Absolutely. So let's start there. That's good. So we need eggs, flour. We forgot sugar. Got to have sugar. So let's start. Who here, you need salt too. Who here has tasted raw flour before?
Yeah, it's gross.
Yeah. So does raw flour taste like cake?
No.
No. Who here has tasted sugar before?
Yes.
I used to do a spoonful of sugar when I was a kid.
Oh yeah.
Medicine
Yes.
go down. Just kidding. Sorry.
Does sugar taste like cake?
Mm, not completely. No.
Close.
They're both sweet, right? But they don't.
Sweet, right? Sweet.
Yeah. If sugar tastes like cake, you wouldn't bake a cake. That's a lot of work to get to taste sugar.
This picture.
So flour doesn't taste like cake. Sugar doesn't taste like cake. Who here has been brave enough to try vanilla extract?
Oh,
I have. It's
very
not great.
strong.
Oh,
Yeah,
it's bad. It's bad.
bad.
It's really bad. Does vanilla extract taste like cake?
No.
Not even close.
Not even close, right? And if it, yet again, like if you just tasted vanilla extract, like, oh, this is an ingredient, I'm going to put this in your cake, everybody would be like, no, thank you.
No.
Right? So it doesn't taste like cake. The point I'm making here is that no one ingredient that goes into cake tastes like cake. And even if you knew what all those ingredients tasted like
Independently.
independently, it still doesn't taste like cake. And you can't cobble together the experience of cake from just tasting them independently.
Mhm.
All right, so doing that doesn't get us the experience of eating cake. So let's mix it together. Let's mix it together in the right proportions. We're going to mix all of the ingredients in a bowl as directed by the recipe. Mix it together good. Now what do we have?
Batter.
Cake batter, right?
Mhm.
Does cake batter taste like cake?
Not there yet.
No, but I mean it's not
Almost there.
100% terrible.
Almost, right? It tastes more like cake than any of the one ingredients do. Or knowing what all the ingredients do. And if it did taste like cake, yet again, we wouldn't have cake batter ice cream. We would just have cake ice cream. There's a reason we like cake batter. There's a reason we like to lick the spoon or raw cookie dough, right? We could do the same thing with cookies. So cake batter doesn't taste like cake. And somebody set it up above, you need to add heat. Zach said we need to add heat. Exactly. So we're going to bake it for around 35 minutes at 350 in the oven. We're just going to do, a single layer cake. So we bake it, get it out of the oven. Now we got cake, right? We ice it up beautifully. You can eat it, maybe a buttercream. Sounds good right now. Eat cake. Now we can know what cake tastes like, right?
Yes.
Yes. We're the cake. Every organism is the cake. And let me illustrate that further. Can you know what sugar tastes like by eating cake?
Nope.
Can you know what flour
No. tastes
tastes like by eating cake?
No.
Or vanilla extract? No, of course not. Yada yada. I'm not gonna waste your time here. At the end of the day, you not only can the constituent parts of cake not tell you what cake is like, eating cake cannot tell you what the constituent parts are like. The cake is a result, a consequence of a series of processes and relationships and context. So are organisms. So you can't, this is like, I think where the big power of anthropology comes in, because anthropology is the study of humans, period. Everything that has to do with humans. As the article that you read last week, I think really effectively argued. And we see humans as the cake, as a set of all of these constituent parts made up. These parts are obviously like the physical, our eyes, our hair, our limbs, our organs, our genes, our chromosomes, our hormones, all of those things. But it's also our history. It's the family you were born into. It's the culture you live in. It is the language you speak. It is our evolutionary history as a species. It is how we relate to the other beings around us, not just taxonomically, like how we relate evolutionarily to other beings, but like your relationship to your dog, the relationship to the birds in your backyard, your relationship you have to the ground, like all of those things go into making you. I mean, your sexuality, your gender, your biological sex, the people you know, right? All of those things are the constituent parts of you. And anthropologists are interested in understanding humans as whole beings, the cake. And when you're studying evolution, you can't study the evolution of the eye without understanding the context in which the eye was
Element.
evolving, without understanding the body in which the eye was evolving at. And so we can think about the difference between a human eye and the eye of a jellyfish. Who here knew that jellyfish had eyes?
I think I probably knew that. I don't know.
They do. They're flat. They can only detect light and dark. But our eyes are cup shaped and they have a lens. So it focuses the light. So we can see shapes. It's not just movement and light and dark. We see shapes. We have rods and cones, which show colors. Mantis shrimp has different kinds of eyes than us. An octopus has different kinds of eyes than us. A spider has different kinds of eyes. Those eyes evolved in their own evolutionary paths. And so you have to understand the bodies in the context in which eyes are evolving. It's much more complex than just like, okay, we're going to study eyes and how an eye evolved. You can't do that because it's like part of a body, and that body is a part of a history, and that history is part of broader geological history.
Who thought of this cake metaphor? Because it's really comprehensive.
Yes.
Like it makes it easier to understand.
I'm so glad, and that makes me feel good because I've used it for a few years now, and it came from a book by Richard Lewontin, who actually unfortunately just passed away. I think you're going to read something by him soon, maybe next week. Richard Lewontin, Stephen Rose, and another person. And Stephen Rose is the only of the three that are still alive. And they use the cake metaphor to talk about like how to understand evolution. And I was like, holy cow, like I've never understood evolution better than reading this 3 sentences in a book. So that's why I've used it. So let me see.
The only bad thing about this metaphor is that it's making me hungry.
I know.
Yep, me too.
See, we don't have cake.
Oh, everybody wants cake.
My daughter and my partner are out there making Greek food right now, and so I can smell it, and I'm already salivating. And then I'm talking about food, which is definitely making it worse.
Mm.
All right,
I'm
so
gonna red velvet after this.
oh, nice. Let's skip over the science and religion for a second because there's a short video I want to show you with a preamble before. And then if we can't get to the science and religion thing, we have Thursday. We get to be together again twice a week. It's so lovely. So we're going to talk about evolutionary theory because understanding evolutionary theory is necessary for doing biological anthropology. As Dobzhansky said at the beginning of this PowerPoint, nothing in biology makes sense except in the light of evolution. However, since you are doing biological anthropology in this class, you need to have a foundation in evolutionary theory. But I don't know how many of you are going into biology or the medical field or something like that. For all of you that are not doing that, you don't need to be an expert in evolutionary theory. Who here is an expert in the physics and chemistry of a combustion engine? Like you can do all the math, you know, all the chemical reactions that are happening in a piston when gasoline is mixing with air and a spark. Who can just walk us through it?
Nope.
Yeah, exactly. And yet you still drive cars, or most of you at least drive cars, or people do still drive cars that don't know that stuff, even if you don't drive. Evolutionary theory is exactly the same way. You don't have to be an expert in evolutionary theory to benefit from the things that people that use evolutionary theory in their research and practice do. Just like you don't need to go learn how all the chemistry and physics of a combustion engine before you can drive. You don't need to learn evolutionary theory before you can get a vaccine, before you can take antibiotics, before you can get a hip replacement, before you can get a knee replacement, before any kind of treatment that you have, because all of medicine is informed by evolutionary theory. And so you benefit from it, and you don't need to know anything about it to benefit from it. Just like you don't need to know about your engine. You should know a little bit about it because you don't want to have to pay somebody to do minor things, but about your engine. But yet again, and one of the reasons why is because we live in a world with other beings, and other beings are evolving, and some of those other beings make us sick. And so we're going to watch a really short clip of E. coli evolving in response to exposure to antibiotics. E. coli is a bacteria. It actually lives inside your nose. It lives on your skin, but you have an immune system, so it keeps you from getting sick. It also, like, we have a kind of semi-symbiotic relationship with it, but it can make you sick if it gets out of control. But let's watch this video really quick. This little clip really quick, and you'll get to see evolution happening in real time, natural selection, one particular kind of evolution happening in real time.
So what we ended up building was basically a petri dish, except that it's 2 feet by 4 feet. And the way we set it up is that there are 9 bands, and at the base of each of these bands, we put a normal petri dish thick agar with different amounts of antibiotic. On the outside, there's no antibiotic. Just in from that, there's barely more than the E. coli can survive. Inside of that, there's 10 times as much, 100 times, and then finally the middle band is 1,000 times as much antibiotic. And then across the top of it, of course, thin agar, the bacteria can move around it. The background is black because there's ink in it, and the bacteria appear as white. First, you see they spread in the area where there's no antibiotic up until the point they can no longer survive. Then a mutant appears on the right. It's resistant to the antibiotic, it spreads until it starts to compete with other mutants around it. When these mutants hit the next boundary, they too have to pause and develop new mutations to make it into 10 times as much antibiotic. And you see the different mutants repeat this at 100. And after about 11 days, they finally make it into 1,000 times as much antibiotic as the wild type can survive. And so we can see by this process of accumulating successive mutations that bacteria, which are normally sensitive to an antibiotic, can evolve resistance to extremely high concentrations in a short period of time.
All right, I'm gonna stop sharing it. So let me exit out of the PowerPoint. So in short, from that, I mean, that was a really short clip. But in short, like, it's really important that we understand how evolution works, because like antibiotic resistant infectious agents are scary. There are multi-drug resistant forms of tuberculosis, of gonorrhea that are around. There's extremely drug resistant forms of tuberculosis around. And so for bacterial infections, these are really big concerns that epidemiologists have to contend with. It is creepy in a pandemic. Luckily, viruses don't viruses. I mean, you can't use antibiotics against viruses because antibiotics only work against biotics, aka bacteria. Viruses aren't alive exactly, and so antibiotics don't work against viruses. I think Melissa, you were going to say something.
No, this is just really interesting illustration of how it worked. Yeah, and how it kept evolving and mutating. You're right, and adapting to its environment. And that's it. Sorry.
No problem. I love when people chime in. Yeah, so it's really important that like we understand these processes and we have a really good understanding of these processes, because we can, in the kind of world we live in today, get overrun by infectious diseases. And so we have to like think about ways that we can attend to it. The fuel that, Zachary, thank you for saying that, because this is a point that I want to make. One of the ways that the narrator of that video is misleading is he says they develop mutations, but he's not very clear on what he means by develop. The bacteria are not like choosing to mutate. Bacteria are reproducing really fast. That's why it's super easy to see this happen in bacteria, because the length of generations are really small because they just clone themselves. But every time they clone themselves, mutations occur in the cloning process. And those mutations can be, they can be neutral and confer no reproductive advantage or no advantage to surviving and reproducing in that environment, aka the antibiotic amount of antibiotics in that space. They can be deleterious, is the fancy word. It just means they're bad. And so they allow you, they basically make you not survive in that environment, or they can be advantageous. They allow you to better survive and reproduce in that environment. And this may be because it makes you have a mutation that just makes you more efficient at like using energy or extracting energy from your environment. In the cases here, you're seeing mutations that randomly arise, because mutations come about randomly. randomly arise. And it just so happens that some mutations that happen confer an advantage in the spaces with the antibiotics. Another thing they don't say is that as they accumulate mutations that first break, they go from 0 into some antibiotics. Some, you get the mutants that happen, and then they colonize that whole, a couple of mutants might come, but they colonize that whole band. And then if you notice, it took longer to go from band 1 than from band 0 to band 1 than it did to go from 1 to 10, 10 to 100, and then 100 to 1,000. The reason being
Kept
is
getting
those
stronger.
random mutations at the beginning conferred an advantage to exposure to antibiotics.
Mhm.
Organisms that were best able to deal with those antibiotics had an easier time going up a level each time. And so it was able to happen faster. So it's not like every time they have to come up with new mutations. They've already accumulated these mutations through random mutation when first exposed to the antibiotics. It's just that now they're being selected for traits that are even better at allowing them to survive in the face of exposure to antibiotics. And so they're able to colonize these areas that have a greater proportion of antibiotics in them. Exactly. So they, so what they started off with, so E. coli is easy. You can pick your boogers and get E. coli from it. One of the reasons that you or your children should not eat their boogers. It's all other than just being disgusting. So the experimental design was you have no antibiotics in a band. You add antibiotics into the band, and then you increase, and you figure out how much antibiotics to put in the first band by figuring out how much it takes to kill the wild type. So as soon as you figure out how much it takes to kill the wild type, you just put a little bit more than that, and that's your first band. And then math is easy. You do 10 times that amount, and then 100 times that amount, and then 1,000 times that amount in the middle. So the research design is really kind of ingenious and very simple, but like in a good way. And so that's a big concern. So it's important that somebody, like, there are people working on these issues and they really have a good handle on evolutionary theory. But if you're like going into business, or you are going to be an EMT, or you're going to do, like, you probably not going to need to be an expert on evolutionary theory unless you just think it's kind of interesting and you want to learn about it. But in this class, we're biological anthropologists, and so we need to at least have a kind of foundational understanding of evolutionary theory, so we can do stuff in the class and have conversations and understand other material that we're going to engage with later in the semester. Does that make sense?
100%.
Good. And something else I want to point out, and this is good because we got like 5 minutes left. This will lead us into our conversation on Thursday, since I didn't get to it today. Like, evolutionary biologists, biological anthropologists, like, nobody's trying to convert you to some, like, if you're religious, nobody's trying to convert you to like some evolution religion. Like, just like nobody's trying to convert you to like a hammer religion, or, like, I don't know. I got a circular saw fairly recently, and it's like, I just want to play with it constantly. Like, it's just like science and evolutionary theory, they're just tools. So there's no like conversion to it. There are assholes like Richard Dawkins that are trying to convert people to to belief systems. I'm not going to say weird, because no belief system is that weird to an anthropologist. There's some pretty weird stuff out there. Richard Dawkins isn't trying to convert people to like evolutionary theory, religion, or whatever. He's trying to get people to stop believing in God because for whatever reason, he wants people to do that. Most evolutionary biologists, there is no evolutionary biologist that I know, and I know a lot, that care. Mostly we just want you to be good people and like have a fulfilling, meaningful life. And if religion does that for you, then you should do that. And that's definitely true for every anthropologist I've ever met. And I've worked in evolutionary biology departments and taking classes with other people and stuff. And everybody's kind of on that same page. So it's this weird kind of pop culture, Richard Dawkins, Sam Harris kind of people that are trying to like argue, but generally scientists want you to just believe whatever you want to believe and be a good person. I think just like most people just kind of want everybody to not be a jerk. As we say in North Carolina, I don't know if this is an aphorism here or not, but like, just don't be hateful. Don't be ugly to people. Yeah, and so like I'm not trying to convert you to evolutionary theory. I'm providing you with a tool set. And if this is a useful tool set for you to use in your career, that's awesome. But if you're not going to be a biologist and you're not going to be in medicine or any of that stuff, it's a tool you get to play with in this class and then move on. And if it's something you find really interesting, you figure out ways that you can use it in your career. Now you got an extra tool in your toolkit that you're carrying to work with you, you know? Yeah, I mean, exactly. And science is a tool. Science is a tool. Yet again, there's no like science religion, although there are people that are like, there's this thing called scientism, which is the thing that science is the belief that science is the only way to produce like real knowledge. But it's super easy to refute that. There are people that hold that position. Richard Dawkins is one of them. But like, am I holding an AirPod case? I'll even show you. There are AirPods inside. Am I holding an AirPod case right now?
Yes.
Yes.
Yes. Now you know something, and it took no science. It's not. See, it's got the little fancy Apple stuff on the back. I don't know if you can see the words, but anyways,
That is a fact.
it is a fact, right? And you know something now, and it took no science whatsoever to know. You didn't have to like do an experiment or generate a hypothesis or come up with a scientific question or whatever. You just looked at my hand and I told you this is AirPods, and you trust me to a degree, and you can see, you know what an AirPod case looks like, probably, and you trust me. And so now you know that I'm holding an AirPod case. No science required. So yet again, that's easy. That's an easy to refute position. Yeah. So if you are Christian or Muslim, or I've had Hindu students before, I've never had a Buddhist student here at Northwest Vista, but I've taught them before. I've had students that were I've had a lot of Sikh students. You do you, man. Yeah, I do have my cool PlayStation in the back. Please believe the thing that makes your life fulfilled and gives you meaning. I'm not religious. I'll go ahead and tell you that, but I respect religion and I respect your beliefs. And as long as you don't use them to hurt other people or be hateful and ugly to other people, I will support you in your belief system. And most scientists, including anthropologists, will do that too. They're not trying to be jerks and like unsettle you from the things that are meaningful to your life. And if you're not religious, we're going to talk about religion, and you should learn about religion because you live in a world with people that are religious. So you should know something about your brothers and sisters' lives, the people that you share this world with. That's all I have to say for today, since we don't have enough time to talk about science and religion. But bet on Thursday what we're going to do. That's what we're going to talk about first. Second, we're going to do an activity in groups, and then we're going to have a conversation about that activity. So that's all we're going to do on Thursday. So be here because it's a really cool activity. You'll get a little bit of a feel for some of the scientific process and kind of what you do. You get to use facts and inferences. You get to generate scientific questions. So it should be a good activity. And I'm looking forward to seeing what you have to say. Just remember, get your readings done, do your reaction statement. That's your assignment this week. And if you have any questions or want to talk about anything, let me know. We can set up a meeting. Otherwise, I'm super excited to see you all on Thursday.
Cool. See y'all Thursday.
See ya.
Professor.
It's a good one.
Bye. Thank you all.
Go get some cake. I'll see
Thank
you
you.
later.
Bye. Thank you.
Bye.
Give a piece for me.
Go have cake.